Hello everyone, this is part 2 of solving a system of linear differential equations using Laplace transforms. So first move, take Laplace of both sides, use the linearity property, and convert the equations in terms of functional notation. So the Laplace of x prime of t would be the Laplace of x of t, and then plus 2 times the Laplace of y of t. And then we have the second equation, Laplace of y prime of t is equal to the Laplace of x of t, and then plus the Laplace of e to the negative t. Okay, so apply the Laplace transformations for x prime. It's s uppercase x of s minus lowercase x of 0 equaling Laplace of x of t is uppercase x of s, and then the Laplace plus 2 times the Laplace of y of t is uppercase y of s. And for the second equation, Laplace of y prime of t, s uppercase y of s minus y of 0, and that's equal to the Laplace of x of t, which is x of s, and then plus the Laplace of e to the negative t. So this should be a familiar one, but use your table, and we have e to the at transforms to 1 over s minus a. So here a is negative 1. So therefore 1 over s minus a minus 1, or 1 over s plus 1. Okay, so now I'm going to move to the right to try to save some room. And what we're going to do at this point is just plug in the initial conditions. Well, the initial conditions are both 0, so that's kind of convenient. We get s x of s equaling x of s plus 2 y of s, and similarly s y of s equaling x of s plus 1 over s plus 1. Okay, so now to set it up in standard form where Cramer's rule can be applied, remember we're going to bring all the terms containing x of s and y of s to the left and set it up so that we have the x of s in one column and the y of s in another column. So when I move this x of s here to the left, it joins this s x of s, and we can factor out an s minus 1. So the s coming from the s x of s, and the negative 1 coming from this transposed x of s. And then we'll have to transpose the 2y as well, so minus 2y of s. That'll be equal to 0. And then same idea here. Well, actually not much to do, just bring over this x of s, so minus x of s, and then looks like plus s y of s, but that'll equal the 1 over s plus 1. Okay, so now it's set up so that we could use Cramer's rule. So I'll start by calculating the denominator. So that's going to be peel off the coefficients, s minus 1, negative 1, negative 2, s. We get s squared minus s. Let's see, this would be plus 2, so minus 2. But then that factors neatly as s plus 1 and s minus 2. Okay, so now to solve for x, the numerator of x is going to be replace x by the solutions, 0, 1 over s plus 1, leave the y's alone, negative 1, s, and so we get 0, and then minus and minus 2 over s plus 1 is just 2 over s plus 1. Okay, so then I want to just take care of solving for x completely like we did in the last example, and then we'll do the same thing over again for y. So now we could say that x of s, okay, it's the numerator of x divided by the denominator, so 2 over s plus 1 divided by the s plus 1, s plus 2. But now that becomes, however you want to think of it, invert this and multiply, invert the denominator and multiply, or this s plus 1 basically just gets absorbed into the denominator here. But we get 2 over, then there's 2 factors of s plus 1, so s plus 1 quantity squared times s plus 2. Okay, so now we need partial fractions on that. So now 2 over s plus 1 is the quantity squared times s plus 2. Alright, here's a situation that hopefully you recall. This is considered to be what we refer to as a repeated factor. Oh, and this was s minus 2, I'm sorry. Kept on recopying in the last two, s plus 2. That should be an s minus 2, but no harm, because it didn't affect any of our computations yet. So that's an s minus 2. Okay, so therefore, with this repeated factor, recall that we're going to have as many fractions as is the power on that repeated factor. And in the first fraction, that repeated factor to the unique factor to the first power, so just s plus 1 to the first, or s plus 1. And in the second fraction, that factor to the second power, and then we could stop because there's only 2 powers. And what goes above each of those is whatever makes the unique factor proper, and since the unique factor was linear, just constant terms. So that was a special situation, hopefully, that you recall about partial fractions. And then we have the s minus 2, and that's linear, so just a constant above that. Alright, so now the working equation, 2 equals a times the s plus 1. One factor cancels, so we have an s plus 1 and an s minus 2 left over with a. With b, both factors of s plus 1 cancel, so it's just b times s minus 2. And then with c, the x minus 2's cancel, and we have s plus 1 as a quantity squared. Alright, so now we need to solve for the constants, and kind of do it off to the side here. First I could use the elimination method. To solve for b, I could let s equal negative 1. You want to use the elimination method first, and then go to comparison if you need to. And on the left we get 2 equaling term containing a and the term containing c goes to 0. So we just have b times minus 1 minus 2. So therefore 2 would equal negative 3b. So b is negative 2/3. Okay, and then to solve for c, we could let s equal 2. And we get 2 equals, okay, the terms containing a and b both go to 0. And then we have c times 2 plus 1 squared. So then C is equal to, let's give us 2 equals 9C, so C is 2/9. Okay, and then we just need to solve for A, and that would be done by comparison. So if we compare, let's say, well, the S squareds look good because that's the highest power of S, and A is associated with that. So compare the S squareds. On the left, we have 0S squared. On the right, we have an AS squared, but notice that B is not involved with an S squared. But C is, because if we square this, we get S squared. To divide out the S squared, 0 equals A plus C. C was 2/9, so 0 equals A plus 2/9. So then A is negative 2/9. Okay, so now the solution for x of s is into the partial fraction decomposition that we had right here. A over s plus 1, so minus 2/9 over s plus 1, and then plus b was minus 2/3 over s plus 1 is a quantity squared, and then plus c, which was 2/9 over s minus 2. So now x of t is the inverse Laplace of this. I suppose this step you could actually skip and go right to using the linearity property and setting this up. If I run out of room, maybe I'll do that when we go for the y's, but I'll take the time to show that there. Okay, so now x of t is now the linearity property minus 2/9 inverse Laplace of 1 over s plus 1. Minus 2/3 inverse Laplace of 1 over s plus 1 as a quantity squared, and then plus 2/9 inverse Laplace 1 over s minus 2. And so x of t then is equal to, so we have minus 2/9, and again this one should be familiar with by this point. 1 over s minus a again converts to, here we are, 1 over s minus a converts to e to the negative at, so that's a familiar one. So that's a is negative 1, so e to the negative 1t, or just e to the negative t. Okay, then we have this next one where there's a power in the denominator, s plus 1 squared. And this one we haven't used before, but if you look down the list, well, actually it's the next one after e to the at. So we have x minus a to the n plus 1th, and an n factorial in the numerator is t to the n e to the at. So if we have s plus 1 quantity squared, that means, okay, so that means that n is 1, and we do have the 1 factorial in the numerator, that's satisfied. So n is 1 and a is negative 1. So this would be minus 2/3 t to the first, because n is 1, and e to the a is -1, so e to the -1t, or just e to the -t. And then finally plus the 2/9. And then here a is 2, and so that's just e to the 2t. Okay, so that's the solution for x of t. Suppose maybe I'll just draw a line there. And now we have to pretty much do the same thing all over again from this point on for y. So n sub y, determinant, leave the x's alone, so the x's stay as the s minus 1 and the -1, and the y's are replaced by the solutions, which was 0 and 1 over s plus 1. So then that gives us just s minus 1 over s plus 1. So this product, and then that product, of course, is 0. And so therefore, y of s is going to be at s minus 1 over s plus 1. Well, let me, if you want to do this, I don't know if this is really all that necessary at this point, but if you want to be this explicit, n sub y over d. Okay, so that's the s minus 1 over s plus 1 that we just found, over d was back up here, s plus 1, s minus 2. Okay, so similar to last time, think of inverting this denominator, multiplying, or that this s plus 1 gets absorbed, however you think of it. We'll get s minus 1 over, now 2 factors of s plus 1, so s plus 1 squared is quantity squared times the s minus 2. Okay, and now it looks like it's pretty much the same type of partial fraction decomposition. So set it up for partial fractions. So we have s minus 1 over s plus 1 squared, s minus 2 equal to, again from the repeated factor, 2 fractions, one with x plus 1, one with s plus 1 quantity squared. What goes above them are just constants, so a and b respectively. And then for the s minus 2, it's linear, so just a constant term called c. The working equation, clear the fractions, s minus 1 is a times, and then we have s plus 1 canceling, but there's one more left over, so s plus 1, s plus 2, b times, both factors of s plus 1 cancel again, so s minus 2, and then plus c times, s minus 2's cancel, we get s plus 1 quantity squared. Okay, so then again I'm going to move up here, try to save some room, and we'll let s equal -1 again to solve for b, and on the left we get -1 or minus 2 equaling a goes away, so does c, b times -1 minus 2, so then minus 2 equals minus 3b, so b is positive 2/3. Alright, let's let s equal 2 now, and we'll be able to solve for c. So on the left we get 2 minus 1 or 1 equaling c times, because the a and b terms go away. Oh, I wrote an s plus 2 here, I'm sorry. That should be an s minus 2. but the a and the b terms go away because we're plugging in a 2 for s, and s minus 2 is a factor of those. So c times 2 plus 1 squared. So that is 9c, because that's 3 squared is 9. So c is 1/9. Okay, and then to get a, we can compare the s squareds again. And so on the left we have 0s squared, on the right an as squared plus a cs squared. So then 0 equals a plus c, but c we already know is 1/9. So 0 equals a plus 1/9, and a is negative 1/9. Alright, so now to the partial fraction decomposition. Our solution for y of s is a over s plus 1. A was negative 1/9, so negative 1/9 over s plus 1 plus b 2/3 over s plus 1 is a quantity squared, and then plus c 1/9 over the s minus 2. And so y of t then is going to be the inverse of Laplace of this. And here again is where you can skip this step and jump right to using the linearity property. But showing it more explicitly, then we have y of t is, okay, factor out the coefficients. So you get negative 1/9 inverse Laplace 1 over s plus 1 plus 2/3 inverse Laplace 1 over s plus 1 is a quantity squared, and then plus 1/9 inverse Laplace of 1 over s minus 2. And similar to the x's, what we had to do when we solved for the x of t, this is 1 over s minus a again. So minus 1/9, a is negative 1, so e to the negative 1t, or just e to the negative t. Here we have plus 2/3. Okay, this is that one that we hadn't used before, the s minus a to the n plus 1th in the denominator. So once again, note that n is 1, and the numerator is satisfied because 1 factorial is 1, and that becomes t to the n e to the at. So n is 1, and a is negative 1. So, therefore, t to the first, or just t, e to the negative a, e to the negative 1t, or just e to the negative t. And then finally we get the plus 1/9. And this fits the form of 1 over s minus a again, where a is 2. So that becomes e to the at, or e to the 2t. Alright, so a little bit involved, but nothing that we can't handle. And so that's the end of systems, and now we're going to turn our attention to your favorite topic from Calculus 2, which is series. So we'll come back and we're going to look at series solutions to differential equations to finish off the course.